Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
How are we going? No. Well, that's disappointing. Sorry about that. Okay, so we're going to use the traditional method. So let's go on with hypothesis testing. I think I should give you really a run-through of all of the hypothesis tests that fit into our current framework that we can be expected to do. So hypothesis tests. And as we said, there's really a number of ways of doing this. And although we talked about proportions last time, I'm just going to run through that quickly. So for proportions, and there's a lot of commonality with the confidence interval section of the course, but not identical, because in the case where you have a null hypothesis, you can use something slightly more precise than standard error, which is the P0. So unknown proportion P, and then you have if the observed n observations and k, and we'll call these the proportion of successes, just in the absence of a better name than success. And we'll observe k of them are successes, which is random, and so p hat, as we always call it, is k over n. And then the estimated, well, okay, so the exact, why did it do that? The exact test, which is the first one, would be to say that you simply have, k is exactly binomial np. And then to execute that test, the p-value is, so there are always one-sided tests and two-sided tests. So I'll do one-sided in which h0p equals p0, h-a-p greater than p0. Then the p-value is the probability that k is greater than k. I'll do k subscript obs for observed. So, because in the context of an exact test, this is kind of, and sorry, I should say greater than or equal to. That's quite important in the discrete case, because it's the probability of getting as bad or worse an observation. So, because we're looking at the alternative being that p is greater, we couldn't care less if k was less than k, so it's only k greater than or equal to k observed. That's the p-value. And so, if you were doing it exactly, you'd either type it into R, or you do this summation at k equals k observed up to n. You actually write it out, n choose k. P0, remember, the p-value is always the probability evaluated under H0. That's the definition of p-value. P-value will never give you a probability under the alternate, because we're saying, supposing the null hypothesis to be true, what would be the probability? P0 to the k, 1 minus P0 to k, n minus k. Okay, so you just calculate that. So clearly that's too much work in many cases. If k was 30 and n was 100, you'd be adding up 71 numbers. So too much effort. So the approximate test, which is good enough for most cases. So this would be the one-sided case. The two-sided, it's even more complicated. So that's the one-sided case. Two-sided case is the p-value is the probability that the distance from the expected value is greater than or equal to what you observe, k observed minus n p0. So that's even more things to add in principle. So the approximate test. So by the way, a two-sided test will get a higher p-value compared to the one-sided test, given the same observation. The reason is, unless the observation is on the wrong side of the mean. If you have a one-sided test and you have an observation, like if your one-sided test is that p greater than p0 and your observation is to the left, you'll get a p-value bigger than a half often. So that's the case where you definitely do not reject the null hypothesis. But in the case where you might reject the null hypothesis, where p is small, then in that case, the two-sided test will have double the p-value, roughly, double the p-value of the one-sided test. So that's the reason why in a one-sided test you should have some reason for believing that, just like a null hypothesis, you have some reason for thinking that that's a reasonable null hypothesis. You also, in the one-sided test, have some reason for only caring about one side. Perhaps the reason is, everything is fine. If p is an error rate, and we want to make sure an error rate is not too big, then we would be quite happy if p was less than p0. We would only be concerned if p was proven to be greater than p0 by this test. Okay, so the approximate test, which is more practical, certainly in the exam, uses that k is approximately normal with the same mean and same variance, p1 minus p. Now, it's often good in this case, so in that case, probability, the p-value, I'm going to do the one-sided. Now, in one-sided, I have been doing the one-sided test for, you could call that a right-sided test for p greater than p0. The left-sided is the same with inequalities reversed, so I'll let you do the corresponding things for that. But I'm doing the one-sided, in that case, where it's a right-sided test. The p-value is the probability that k is greater than or equal to k observed. I'm just going to, you could straight away plug that into the normal approximation, but I'm going to suggest for this one sample proportion test, I'm going to suggest you do something different, which is in the discrete setting, k is a number. So to say k is greater than or equal to k observed, that's just as good as saying that k is greater than, or greater than or equal, it doesn't matter, k observed minus a half. So those are exactly the same because k observed is a whole number. It's like 3. So in the example where you observe 3, you say the probability k is at least 3. Convert that to k strictly greater than 2.5. Now, why would you do that? It tends to give you a slightly better approximation. Since it's approximate after all, it's not always better, but it tends to be better. So this is called the continuity correction. Continuity correction. That's a very standard name for it in the context of normal approximation to binomial, also normal approximation to Poisson. So the reason that's the case is if you just imagine the binomial is a rather kind of blocky distribution. Okay, probably looks a bit more like this. And then supposing that this binomial is well approximated by the normal curve, which it actually is. If it's well approximated by the binomial curve, then you're going to get a better approximation to this. So the tail area that we want, let me shade it in red. The tail area that you want, if this is k observed, I'll just label k observed is actually sort of in the middle of this histogram. Because the histogram is well approximated by the curve, and that means we should make the histogram boxes centered on the corresponding points. That's kind of the closest approximation. This is heuristic, but it tends to be true in most cases. It's sometimes not true very far into the tail, but it's mostly true. So you get a better approximation. If I'm trying to approximate that by the area under the curve, the best approximation of the area under the curve is to sort of start at roughly the same point here. And that point is actually k observed minus a half. When you do that, there's a little bit above, a little bit below, a little bit above, a little bit below. They don't exactly cancel out, but they tend to cancel out better than if you had just done the area over that way. So because this is exactly the same, we'll say by the normal approximation, probability that z, which is a standard normal, is greater than I have to do k observed minus a half. That's the relevant cutoff. Subtract the null hypothesis mean, and divide by the null hypothesis standard deviation. Root NP0, 1 minus P0. Okay? So the only difference with the... so you can look that up in a normal table. That's, if you like, that's 1 minus 2 phi. Phi is the thing that's tabulated in the standard normal distribution thing, and you just put in k observed minus a half minus np0 by square root np0, 1 minus 2. Now, it's not a disaster if you forget the half. In fact, it's almost the same for large n, and it's not always even better to do this. But as a general rule, for a single proportion, you might as well do that correction. It can improve your result. So, now let's just do the two-sided in the same context. It is still probability that k is greater than or equal to k observed. It sort of depends whether you want to do the continuity correction or not. It's a bit harder to do the continuity correction because if k observed, if the mean np0, if that's either an integer or half of an integer, then the continuity correction works just the same. If it's not half of an integer, then you have to do it separately on the left and right hand intervals. So I'll just give you the approximation. Sorry, that's not actually the p-value that you want. You of course want probability that the deviation you observed in p0 is greater than or equal to the one that was seen in this particular example. Okay, and so I'll just say without continuity correction, it's roughly. Sorry, that shouldn't have been 1 minus 2 pi. That should have been 1 minus 5, and that's. So in this context, because it's a normal distribution roughly centered at np0, which should be here, then you just get twice the p-value, as I said before. So it would be, let me just say, 2 times 1 minus phi of, let's do the absolute value of k observed minus np0. So that is without the continuity correction. And once again, I'm not going to object if you don't do the continuity correction. It can make it simpler in the case. Square root np0, 1 minus p. Okay, so that would be your p-value. And as always, if the p-value is less than alpha over 2, then less than alpha you reject, and if it's greater than alpha you do not reject. The corresponding rejection regions, which we sometimes call are the rejection region is for a particular observation. I'll say it's for Z because this is the standardized observation. Okay. Corresponding rejection regions are Z bigger than, let's say, Z alpha for right-sided test. The right-sided test is the case where HA is P greater than P0. Z less than minus Z alpha for the left-sided test, which is when HA is P less than P0, and absolute value of Z bigger than absolute value of, well, I don't need to do it. I know that Z, remember that our convention, when I put a subscript here, that's not quite the quantile alpha over 2, that's the quantile 1 minus alpha over 2, because I want a positive number. So that's the right side. So that is the two-sided case. HA, P, not equal to P. Okay. So in the case of two samples, two proportions. So just to remind you of the setup here, the first one is probability P of success. Actually, let's call it P1, and the second sample has probability P2 of success. and they don't have to have the same sample size, n sample size m. If there's actually two cases, now I'm going to assume we've done quite a lot about one-sided versus two-sided, so I'm going to assume in all the subsequent tests you can do one-sided versus two-sided on your own. So we're going to focus on just, I'll always write down the two-sided, but you can do the one-sided. Sample size m, and the relevant statistic, we'll call it z, which is only an approximate normal, but p1 hat. Now, of course, let me say the observed proportion is p1 hat. Okay, so I had k before. I'm not going to use k again because we'll never be doing an exact binomial test for two proportions. The reason is you don't have an exact, even under the null hypothesis, you don't know what binomial it is. So we only ever do approximate tests in the two sample case. And that's p1 hat over minus p2 hat. Now it depends on the null hypothesis. I said before that you could do it with the null hypothesis that p1 equals p2. In that case, your numerator would just be p1 hat minus p2 hat. But you can also do it in the, okay, I'll do it in two cases. The first case is when H0 is that P1 equals P2, okay? If that's your null hypothesis, you use a pooled proportion. I said this at the end of the last time, P hat P. You take the total successes divided by the total observations. Total observations is n plus m. Total successes is n P hat 1 plus m P hat 2. That's your pooled proportion. And you use that pooled proportion estimate for the standard error. The difference, P1 hat has standard error P1 minus P. I'll use the pooled proportion for those. And divided by n in the case of the first sample, because that's the sample size, and divided by m in the case of the second sample, because that's the sample size. And we add the two variances together because these are two independent samples, I guess. I should have made clear that this is a test for two independent samples of two proportions. So, so there's no connection between the people sampled from population 1 and the people sampled from population 2. If that's the case, you're, as always, p-value and rejection region as usual. So that's going to be the same. Once you've converted to a Z statistic, the p-value calculation and the rejection region calculation are the same as normal. By the way, because it's a normal approximation, you can actually calculate a p-value in the exam for this. You can't for t-tests because I don't give you the exact, all the quantiles at t, I only give you a few. But you can calculate a pretty exact p-value for a normal test because I give you the normal tables. So, so this is just probability that, yeah, absolute Z greater than absolute Z observed. In the two-sided case, one-sided you can make the appropriate connection. Rejection region would be absolute value of Z is greater than Z alpha over Z. Same as so that's two independent samples. That was in the case where P0 equals P1 equals P2, sorry. Let's say the case is, you can also do P1 minus P2 is some constant other than 0. See, so there's some hypothesized value for the difference. So I believe that the support of party A is 10% higher than the support of party B. That would be your null hypothesis. If that's the case, your Z statistic is P1 hat minus P2 hat minus C, of course, because under H0 that should be C. Then the sample, unfortunately the standard error you have to use, we used this because there was a meaningful pooled proportion to estimate. But here there's nothing to estimate because P1 and P2 are not the same. So it's not actually useful to do that. That would be biased by the sample sizes and give something that was not useful. So we have to, it's not as good an approximation, but it can still work. So, by the way, for this observation, well, for both of them, you want N and M large enough. And let me just say, for all the tests of proportion that are approximate, you check the rule of thumb. You should be fine so long as each pooled proportion NP1 hat is greater than or equal to Actually, the rule of thumb, you're able to get away with a pooled proportion for at least 10. This is only a rule of thumb. N1 as P hat is at least 10. So that was the rule of thumb in the case where you have a pooled proportion. If you don't have a pooled proportion, and the rule of thumb is, of course, a rule of thumb for whether the normal approximation is even vaguely correct. So then you're actually going to have to check it at least in both cases, NP1 hat at least 10, NP2 hat at least 10, and 1 minus P1 hat at least 10, and 1. So that's a bit boring. So each of the, in other words, each of the observed number of successes and failures should be at least 10 in order to apply the normal approximation happily. Then you do P1 hat, 1 minus P1 hat divided by n, plus P2 hat, 1 minus P2 hat divided by n. Okay, p-value rejection region as usual. So rejection region is the same. As always, this is an approximate test, so that's all you can do. So this is just a slightly better case because you can use pooled proportion. But both of them have a one-sided or a two-sided variant. That's going to be the same. Now, let me talk about a bit more about the Poisson. We talked about Poisson in the context of confidence intervals, and let's talk about tests for Poisson mean. It's actually very similar to proportion. Okay, so one sample. There's once again going to be one. Most of this is going to be very familiar once we compare it to the proportions. So one sample, which would be that you have a number of observations, x1 up to xn, IRD, Poisson, lambda will usually be my Poisson parameter. And we know that x bar is, Poisson has mean lambda, variance lambda, remember? So x bar is approximately normal, lambda divided by n. That's our normal approximation. In order for that rule of thumb, it's actually very similar to the binomial case. We just say lambda at least 10, because that's the expected number of successes. Okay? Now, let's talk about lambda naught, because in the one sample case, our hypothesis will just be that lambda equals lambda naught versus 8a. Now, once again, it can be, I'll do the two-sided case, but you could do one-sided. None of that. Once you've got a normal, you just take the right tail on the left side. Okay, but I'm going to do the two-sided case. The rule of thumb would be that lambda naught is at least 10. And did I mention that in the, let's go back to the one sample proportion test. For this approximate test, the rule of thumb, once again, would be that NP0 at least 10. So you might say, why NP0 and not NP hat? Because if we have a belief of what it is under the null hypothesis, we should use it. That's if you're thinking, remember p-values are always calculated under the null hypothesis. So any approximation is done under H0. So if you know P0, so much the better, you should use it. And the same, that was also why we use P hat P. If we know they're the same, we might as well pull. So that's your rule of thumb to check here. So, by the way, if you get a case where the rule of thumb does not apply, then you would be dodgy kind of to use this. You would know that it's not a great approximation. So you'd probably best go to the exact test in that case. That's all you could do. So I've given you an exact test which you can use in where the rule of thumb fails. But of course the exact test doesn't work for two samples. So then you just don't have anything that is effective. At least nothing that I've taught in this class. So going back to the test for Poisson mean, null hypothesis. Well, okay, so your Z statistic is exactly what you'd expect. Maybe it should be very believable that X bar is the relevant statistic you want. It's actually a fact that X bar in this context is a sufficient statistic for lambda. So if anyone wants to check sufficient statistics, X bar is sufficient. But that's the reason why. So once you know X bar, there's no use to knowing any more information about the Xi's, and so this is the best statistic you can come up with, divided by square root lambda 0 divided by n. Now, that is Z. Okay, so you could do P value would, as always, would be the probability that absolute Z is greater than or equal to absolute Z observed, which is Z observed across the same absolute x bar minus lambda 0 divided by square root lambda 0 divided by n. Yeah? So, and of course concretely 1 minus phi of that value. So x bar minus lambda 0, you can, phi is the thing that is tabulated on the exam. I wanted to, some people have asked about the exam. You do get those 4 sheets of statistical tables that were on the website. They will all be printed for you, so that's something you couldn't bring in. But you can bring in, there will be no formula sheet that I provide, same as midterm. I never provide a formula sheet. But you are allowed to bring in an A4 sheet of your own handwritten notes. So that means they have to be handwritten by you, not photocopied from someone else and not printed out because, even if you say, oh, my handwriting's very big, so it's unfair. Unfortunately, that doesn't count. You have to handwrite it yourself. This is to stop people, putting a treatise into 4-point font and then printing it. So, yeah. So the rule is it has to be your own handwritten formula sheet if you want to bring something. It doesn't have to be formulas. You can write out a poem if you like. But that's what you're allowed to take in. But you will be provided with just the statistical tables, the 4 ones that are on the one-hole side. Okay, p-value is this guy. What else is there to say? Oh yes, one remark about the one-sided. You could even use the continuity correction in the two-sided case, but it's a bit easier in the one-sided case. Can use the continuity correction. Because same as binomial, Poisson is something that takes integer value. So you imagine your Poisson, it's no longer looking like your Poisson looks something like this. It's very unlikely to be. And actually, this isn't a great picture because I said that NP0 should be at least 10. So that's, picture. That should be at least 10 in order to even apply the normal approximation. So the picture's not quite right. But whatever. Okay, maybe I'll put my axis back over here. Okay. And then these are actually each centered on a point. So much like this might be sorry, that actually brings up an important point. I got the rule of thumb wrong, which is, the rule of thumb is actually that n lambda 0 is at least 10. That's less stringent. That's less stringent. The reason is, if I have a whole lot of observations from Poisson lambda, they might each have expected value around 0 or 1. That's okay so long as you have enough observations to put this up over 10. That's important. So by having large enough sample size, you can achieve this rule of thumb for no matter what it was to start with. So that's quite important. Sorry about the mistake. So yeah, so this by the way, another way to write that is that this is actually, this would be the easy way to calculate it, but it is actually the same as the sum I equals 1 to n of xi minus n lambda 0, because just as we have an approximation for x bar, we have an approximation for the sum of the x's, which is n lambda, n lambda. This is approximately n lambda, n lambda, so I'll just write n lambda 0. So those are exactly the same observation. So it is this guy which is an integer valued random variable. Right? That guy, x bar is not integer valued, but this guy is integer valued. So when we're doing something with an integer valued random variable approximating by normal, it's good to use the continuity correction. You don't have to always, but it's good to. So if you use the continuity correction, then you would have, if HA is the, let's do a left-sided case, lambda less than lambda 0, then the p value is going to be the probability that z is less than, not so much z observed per se, but fixing up with a 1/2. So let's write it sum I equals 1 to n xi, and then I'm going to fix it up minus n lambda 0, and then divided by square root n lambda 0, and then I need to either add a half or subtract a half. Let's see how we know whether it's going to be adding a half or subtracting a half. Here is, if we're doing a left-sided test, if we want to get a p-value that is, anywhere low down, this might be sum I equals 1 to n of xi. So it's this observed value here. And so the true area that I want is going to be shaded in red. That's the true area I want. So it actually includes this whole rectangle, that whole rectangle, that whole rectangle. So, moral of the story, when you want a left tail, you have to adjust the endpoint a little bit to the right, precisely 1/2 to the right. So I take this endpoint and I adjust it plus 1/2. That's going to give me, in general, not 100% always, especially if you're in the tail, but in general that will give you a better approximation to the p-value. It can be like a whole order of magnitude better, so in some cases it's better to do. So the plus 1/2 is the continuity correction for left-sided. If you remember nothing else, if you want to do the continuity correction for right-sided, you do minus 1/2 to include. Remember the right-sided would be the same as here. You have the k observed and then you shift that integer a little bit to the left to get a half integer, k observed minus 1/2, and that gives you a better approximation. In the left-sided case, you have your integer, which is the sum of all the Poissons, which is a whole number. You shift it a little bit to the right to get the better approximation. Okay, that's all I want to say about one sample Poisson mean. Let's say two sample Poisson mean. Two sample for Poisson mean. So, yeah, x1 up to xn IID Poisson. I'm going to use, I could use lambda 1 and lambda 2, but I'm not going to do that. I'm just going to use lambda and mu. Y1 to yn IID Poisson mu. Remember that Poisson counts rare events, so this can, it's always an assumption that, you know, before you do your test you have to have your assumption, so you are assuming that the xi's are Poisson. But it's common and very reasonable to make a Poisson assumption in certain cases. Just like if you had heights of, say you had heights of adult men, that's, if you include children and different sexes and stuff, you might get something that wasn't exactly normal. But if you look at heights of just adult men, you're likely to get something very close to normal. That happens whenever there's a whole lot of very small influences that are independent of one another. So in the case of heights, it would be very valid to make the assumption of normality. Similarly, if you said, you know, Geiger counter or something, it might, you know, a number of, well, I don't know, maybe that's a very large number. If you just have something that observes counts of observations, counts of certain rare events over time, you knew it was independent from one time to another, it's very reasonable to assume it's Poisson just on first principles, and the only thing you don't know is the mean of each Poisson. And in that case, we want to use a test like this. So the H0 would be that lambda equals mu, and I'm not going to do the case where lambda equals mu plus something. Let's just do the H0 equals lambda equals mu. Lambda not equal to mu. To test that they're the same versus not. Once again, it would be better to do the pooled estimate, because you're always getting a p-value that is under the null hypothesis. So the pooled estimate would be the probability that x1 plus xn plus all the yi's plus ym, and then divide by the total number of observations, n plus m. So let's call that lambda hat p, pooled lambda. And then you would be expecting nothing other than a z statistic, which would be x bar minus y bar, because that's going to be, x bar has expectation lambda, y bar has expectation mu, and then I subtract 0, of course, because under the null hypothesis they're the same, and then I divide by the variance. Now it would be lambda over n for x bar, lambda over m for y bar, so I have a commonality of lambda hat. I'll use the pooled estimate, 1 over n plus 1 over n. Okay? And then you do the rest as before. So this should be very reminiscent of the binomial case. As always, in two sample case, there's absolutely no way to do any continuity correction. There's also no way to make any reasonable, there's no real way to make any reasonable exact test, certainly not in this class. So that's that. Now let's do the, I guess I can do the two sample, I can do the other case as well. It's very similar to the binomial. H0 lambda equals mu plus constant, HA lambda not equal to mu plus a constant. Oh, you could do one-sided or two-sided, it's the same. Your Z observation would be x bar minus y bar minus that constant, because x bar is expected to be lambda, y bar is expected to be mu. Your mean, now, just as if with the Poisson case, you have to you have to use your lambda bar and your lambda hat and your mu hat separately. Lambda hat, what's our estimate of lambda? It's obviously just x bar, right? Because the expected value of x bar is mu hat is equal to y bar. So in that case, you would just put, okay. Well, should I write x bar over n or y bar? Yeah, I'll write x bar over n, but that's the same as lambda hat over n plus y bar over n. Yeah, that's it. So that's, in that case, it's slightly less precise because you weren't able to pull your estimate. Okay, so that's all I want to say about Python. You could do one or two-sided with that. Let's talk about all the tests for mean and variance. And these are principally designed for normal observations, but they can also, because of the central limit theorem, sometimes be applied when the observations are not normal. Okay, so let me say, I'll do the not normal case before because we've talked quite a lot about t's, but normal approximation. Okay. The normal approximation is if you have x1 up to xn that are IID, some distribution. We don't know what it is. Mean, mu, and variance sigma squared. Now you do have to assume that it actually has a mean and a variance, because of course if there's no mean and no variance, even the central limit theorem doesn't apply. And if some people are really pedantic, you might want to assume maybe a third moment rather than just a third and fourth moment, because a second moment can have a very, if it only has a second moment, can have a very slow convergence under the central limit theorem. But that's a technicality. Normally you're measuring physical quantities which have a natural bound, so then you have no problem. It's only possible to get diverging moments when you have no bound. Like, that can happen with some financial data. So finance is the place to watch out, because in finance you're always chopping and changing and doing little, for instance, price. The thing about financial data, if you have a unit price of an object, that can actually go to infinity, unlike things in the real world. The unit price of an object can go to infinity in the sense where the object runs out of existence and then there's a shortage, and when you can't get anything at any price, that means the price goes to infinity. So then you can actually get unbounded moments, you can get things that don't have normal approximation. But if you're measuring something in the real world, it'll have natural bounds, it'll be fine. So normal approximation, if you have this, x bar approximately normal mu sigma squared over n by the central limit theorem for large n. Okay, I should give the rule of thumb normally for that. Normally we say, it could be 25 or so, let's say n at least 30, different sources say this, but must be higher if very skewed, or heavy-tailed, but if it's very heavy-tailed, it's often skewed. I guess you could have a heavy-tailed thing that was symmetric in both directions. So, but skew sort of counts as a heavy-tail in itself. You might think, because relative to its own mean and variance, it's very heavy-tailed. So here's an example of something that is skewed, but not in the conventional sense heavy-tailed. Just a Bernoulli P, where P is, 10 to the 0, very small. This is skewed. Probably most people wouldn't call it heavy-tailed because it's just within a very, very short space. But it's super skewed, and that would mean that the rule of thumb doesn't work. We can even see that because we know a Bernoulli, the test for a mean of a Bernoulli, where you have IID Bernoullis, we've already done that. That was proportions. And you see the rule of thumb for proportions. Well, it's a bit more lenient, and it says np0 at least 10. So if p is a half, then that's saying only at least 20. But if p is 1/10, that's saying n should be at least 100. So you can see the required sample size goes up as the skew gets bigger. So we've already seen it. So that rule of thumb's a bit useless, but because that works in the case where nothing too skewed. So I shouldn't say that. It's not useless, and if you need some kind of exploratory data analysis, if you do a box plot or something like that, or you just see from the shape of the data that's not too skewed, this is perfectly fine. Okay, so under that rule of thumb, then the okay to do the test for mu, I'd be less less keen on doing the sigma squared this way because it's more subtle, like the sigma squared being chi squared. But even sigma squared can work a little bit in this approximate case. But certainly for mu, you would just say x bar minus mu. Now there's a number of approximate. Okay, so we need a null hypothesis. Let's just test for the mean. HA mu not equal to mu 0. X bar minus mu, it's obviously an approximate z divided by square root. I'd love to do square root sigma squared over n. I can't because I don't know sigma. And you just put in s over square root n. S is the standard sample variance. Okay? Approximately normal 0, 1. So once again, you might say, how did I do that? Well, it's just n at least 30. This is approximate to begin with, so we're not losing in a whole lot extra by replacing s with sigma. Now, if n was 10, replacing s with sigma is dodgy. And if n was 1, then it would just be wildly off. Well, actually, n equals 1, you can't even estimate s. But if n was 5, then this is going to be wildly off. So it's really important that n is large for this. So having said that, then at that point you're at leisure to do that. Now let's go on and do tests mean and variance. So that's all I really want to say about the approximate case. Okay, the normal approximation case, let's do 2 sample of the normal approximation case. So 1 sample is here. 2 sample. Once again, you can even do different variances here so long as you have large sample size. x1 up to xn, they're IID, and not normal, I'll just say mu and sigma squared, so notably not normal assumed here, and y1 to ym, IID, let's say mu x sigma squared x, mu y sigma squared y. Okay, so it's very important that both of these, and you can sort of check by observation mostly, both not too skewed or heavy-tailed. If they're both not too skewed or heavy-tailed, your z is going to be x bar minus y bar, and even if you wanted to do, okay, h naught mu x equals mu y plus a constant. You can do mu x equals mu y plus a constant. Then as normal we do x bar minus y bar minus c, and then just the best estimate you can do. So s squared x divided by n plus s squared y divided by n. So you get to see the pattern here. If the things you're estimating are not the same, don't pull them. Right? So I'm not assuming sigma squared x and sigma squared y are the same. And I should say n and m are both at least 30. Okay. So this is quite important as a rule of thumb. I forgot, of course, to put the rule of thumb in the second case with croissants, but as always I need n x bar at least 10, n y bar at least, or n y bar at least 10. That would be your rule of thumb for going back to the normal basically for Poissons and for binomials, always check that the count is at least 10 and the count from the other end in the binomial case is at least 10. Okay, so that's the approximate, not too skewed and not too heavy-tailed. So the mean and variance of exact. So if you do know that your things are exact or almost exact, so height data is not going to be exactly normal, but it's almost exactly normal mu sigma squared. Then you have exact t distributions. T, which is x bar minus, so the one sample case is this sample, x bar minus mu naught divided by s over root n. That is exactly t n minus 1 distributed. You have the quantiles of that, so you can do the rejection region from the tables. So when you're doing a t-test, you won't be able to get an exact p-value. You'll only get a range, but you will be able to get an exact rejection region. So the rejection region would be absolute value, for two-sided it would be absolute value less than t n minus 1 comma alpha over 2. Or for one-sided, you take the alpha quantile. Okay? So 2 samples.